Hi, David and Franca. It's good to see you both.
Good to see you.
Hi, Lily.
Hi. I was wondering if you could have a bit of a discussion on mathematical methods behind machine learning and artificial intelligence.
Okay, Franca, you go ahead. This is your area.
Sure. Yeah. So I think machine learning, the big advances in machine learning have come through really empirical research, but there's just now the theory is starting to catch up, and I think it's very important that we understand and have some rigorous guarantees for the methods that are being applied.
I mean, this is part of what responsible AI needs to have. If we don't really know what's going on behind the scenes, we don't know what the error terms are. How we're not in control. We don't know what could be going wrong. It's part of the point.
So usually any type of modeling that you're doing, there's several sources of errors, and it's sometimes very difficult to capture all of them in the methods that you're using in such a way that you can actually do analysis and proof guarantees about these methods.
And I mean, just you mentioned the different types of error. You know, in statistics, there we think about error sort of as well, of course. But really, in machine learning, we're looking at errors at many different levels. Do you want to say a bit more about that?
It's not just in machine learning, really, in any kind of data-driven science where you use both data and models. You have, on the one hand, you have inherent errors in your data, so in the measurements that you're taking, and those again have different layers to them. But let's say you have some error in your measurements in your data, then you have errors in terms of the models that you're choosing, and then finally you could have some truly inherent random effects that are part of the process that you're observing. And in many models, such as also ensemble and common methods, like for filtering and sampling problems, often it's easier to bunch all of these together in one error term. And a lot of models is assumed that this is, for example, Gaussian additive noise, when it's actually known that, yes, it's more complicated in real life than just Gaussian additive noise. But in the end, it's very difficult to prove anything about those methods beyond Gaussian additive noise assumption.
Well, and this is just naturally how the maths evolves. I mean, it was in the 1970s that the basic statistical methods went from linear modeling to generalized linear modeling by going beyond the sort of Gaussian noise in the sort of what you called there, the sort of just a natural random error in your underlying model, in your actual phenomena. And so this is just a natural part of the mathematical process as the methods develop to sort of move beyond this.
I mean, the first type of these methods was the Kalman filter in the 1960s that was actually used to get us to the moon. And there, everything was assumed to be linear and everything was assumed to be additive Gaussian noise. And it was very successful at getting the job done, despite these assumptions being very simplistic, of course. But now we are moving forward to actually being able to treat nonlinear settings and also non-Gaussian noise. However, the theory is still far behind the methods. So most of these methods, ensemble Kalman filtering, ensemble Kalman inversion algorithms, are used in geophysics in complicated engineering problems where you don't have linear problems. You definitely have nonlinear problems, and you have several sources of error. And yet there's few alternatives actually what to use, especially in high dimensional settings. So practitioners have to deal with the fact that they know that the methods that they're using are not actually proven to work well in the setting where they're applied. But then, you also have, of course, the experience of the practitioner that comes into play.
And the point is that they can still be responsibly using such methods, which they know to be inadequate in some sense, because they understand and they have the experience of what can go wrong and how to work with it. And you've taken a specific example.
And this is actually a very important, this is actually a very important field of research. I mean, the community is very well aware that there's many gaps to fill, and there's many ongoing efforts and also lots of developments at the moment to push those questions forward, to go beyond Gaussian assumptions, to prove convergence rates for more complicated error terms and for targets also that are not Gaussian.
Absolutely. And the point really, I think, which is so important here is that as a user of this, you can be responsible, even if you're not, that the methods are flawed, but it's the best that's available. And this is what we're having to do, not just in the example you've given, but across a lot of machine learning as well, because the methods are evolving so fast. You know, it's an awareness of what different methods can do and what their limitations are. That's what practitioners need to be responsible.
I mean, the example I gave with ensemble common methods comes from the area of filtering problems and inverse problems. But of course, now if you go to machine learning, I would say that the gap between what we can do and observe empirically and the theory that exists to underpin those methods is even wider. And it's just now starting to happen that there is a more rigorous approach and also an appreciation from the practitioners that this rigor, this mathematical rigor is in fact needed. For example, to understand what are the type of functions that you can approximate, what can you guarantee with the neural networks that you have learned, where can it fail, right? There's these very important examples of how you can trick neural networks. And of course, now there is a whole field developing on adversarial training, like how do you actually inbuild in your machine learning process that you have some robustness with respect to adversarial attacks. But in terms of the mathematics, this is just, it's still a field in its infancy. And I think there's really a lot to do to bridge these different approaches and to also get more awareness, both on the practitioner side and on the theoretician side, as to what is the role that these different ingredients play to give us responsible AI methods in the end.
Absolutely. And I think, you know, again, this course is mostly aimed at the practitioners. So for them, you know, we're not saying that they need to sort of become, you know, people at the forefront of the theory, but they do need an awareness of the limitations of the methods they're using. And that's really the key point here.
Right. I think one thing is to be limited by what is known, but the other thing is to not put in the work to actually be aware of what the shortfalls are. And I think that is very important. Also to help the communication between the different communities so that the theoreticians have an understanding of where are the gaps that matter to the practitioner, where are the questions that really need to be answered. And then on the other hand, for the practitioner to ask the question of, you know, are the assumptions in the methods that I'm using actually well adapted to the problem that I'm.
Exactly. And that's really where the responsible nature comes in. It's about sort of this collaborative approach rather than just, you know, knowing one thing and applying it. And so that's really what we're looking for across the board, is this collaboration where people actually try to speak the same language and understand what it is that people need and what it is that we know.
Yeah, I think one point that I should make is that, you know, when you're on the more end user side or the practitioner side, maybe you feel, oh, there's these exciting AI methods that you can use just out of the box. But to really have an understanding that there's so much research happening and there's so many like knowledge gaps that we're filling step by step, and people that are working on these questions, that is really worthwhile trying to understand what's inside the box and trying to ask the questions, you know, where are the gaps between what this method can provide and what I need for my application.
Yeah, and I think just to be clear, when you talk about going inside the box, you don't mean going that deep into the maths of it. That's not needed for the practitioners, but the assumptions, understanding what the assumptions are, where its limitations are, what you can do with a different method, that is in the realms of sort of what the practitioners should be doing.
Yeah, and maybe just to add a perspective of a mathematician, since I'm coming in from the theory side, you know, when you're trying to develop these methods and you're developing these algorithms, then the choice of assumptions is often driven by what you can actually prove. Like, what are the assumptions that I need to make so that I can guarantee certain things? But maybe those assumptions are not the most useful or adapted to the application. So now it's very important also that the practitioners ask the question of what are the assumptions that I can afford? And what can I afford in terms of which assumptions can I break and which ones can I not break in order to still be confident in what my method is actually saying, the insights that I'm deriving. And there's also, this is very important for these people to talk to each other, because, you know, as a mathematician, if a practitioner comes to me and say, well, this assumption, if you're making this, I cannot use it for anything, then, well, how much time should I invest actually proving something for those assumptions? Whereas if somebody comes to me, if you make this assumption, well, it limits in some cases, but it's still fine, then it's a different story. So I think it's very important that the whole pipeline works as a whole.
Absolutely. No, thank you. This has been very useful. And I hope what this will help give our course users is an insight into how deeply we need to think to be moving the field forward on what we know, what we don't know, and what we're finding out, and how we need this communication and collaboration to be able to sort of get the right information coming out from the mathematicians like yourself to serve practitioners. So thank you again, and this has been very interesting.
Thanks, David.
Thank you both.